IPFS, we can add a new integration test. So we'll call this test IPFS upload.py. Now you might want to write a test for this, and we're not going to do one, but I challenge you to later on maybe come back and write your own test for this upload to IPFS. For now, we're actually just going to manually test it. So we're going to go back up to our script here, and we're going to run image URI equals upload to IPFS image path, and then we're going to get printed an image URL. Since we're working with the St. Bernard here, we should get a St. Bernard image URI. So if I run Brownie, run scripts, advanced, create metadata, network Rinkeby. Let's see what happens. I needed to add brackets here. Sorry about that. Now let's try it again. Awesome. We were able to create this metadata file. Now, if we go ahead and copy this and paste it, perfect. We see exactly what we're looking for. We see our St. Bernard. Awesome job. And this has been uploaded to our own IPFS node. Now, I want to show you guys actually another service and another way we can actually upload these to IPFS. Some people don't want to run their own IPFS node because they're not actually going to be keeping it running the whole time. Anytime their node goes down, this means that nobody will be able to see your image unless somebody else pins your image or uses your image. So what I also like to do is I like to upload it to some other third-party service as well as uploading it to my own IPFS node. So I like to create another script actually called deploy to Pinata. So let's go to scripts, new file, upload to pinata.py. So Pinata is an IPFS file management service, and they actually will pin whatever files that we're working with as well. So we'll have it pinned in our node, and they will have it pinned as well. So we can go ahead and register. Awesome. This is what Pinata looks like. It's a way to upload and work with IPFS, and they'll give us some extra support. And they have a free tier, which is fantastic as well. They have some wonderful documentation as well under this documentation section. So let's go ahead and upload this to IPFS so that when our node goes down, our images don't go down. So we'll do Pinata base URL is going to be equal to https://api.pinata.cloud. And you can find all this in the documentation as well. If we scroll down the documentation, we're going to be using this pin file to IPFS endpoint here. And you can see that entire endpoint right here with the base and then the endpoint. So we're going to copy that endpoint. We're going to say endpoint equals pinning/pin file to IPFS. We're going to choose some file path. And for us, we're just going to do ./image/pug.png. Of course, if you want to upload some other image, you could, change this file path, or you could even do some type of for loop to pin everything in the image section here. Again, we're going to do file name. We're going to use that same syntax as before. We're doing file path .split/ some fancy Python stuff just to get this last part. And we also need to use some headers in this post request. So it's a type post request. We need to use some headers here. So we're going to say headers equals, copy this, Pinata API key, which is going to be some API key. And then we also have this Pinata secret API key, Pinata secret API key, which is going to be something else. We can find these two API keys. If we scroll all the way down, we hit API keys, create a new API key. I'm going to call this, you can make this an admin key. I'm just going to do limit max users, limit max uses. I'm going to set this to 200 because I'm going to make this a public key, so I don't want people using this a million times. Please make sure you select at least one permission. Pin file to IPFS. For those of you guys watching, you can absolutely just grab all of these if you want. You can make this an admin, do whatever you want to do here. Since I'm only going to be using this pin file to IPFS, that's all I'm going to do. Hit create key, and here are our tokens here. So our API key is going to be right here, and we're going to copy that. We're going to open back up that .env, and add this as one of our environment variables here. So we're going to export Pinata API key equal to that key there. This API secret we're going to copy, and we're going to do export Pinata API secret equals that key there. And we actually don't need this JWT, but if you guys wanted to, you could copy it as well. So now that we have them in our .env file, these are now going to be environment variables that we can use. And Brownie is going to automatically put them into our environment. So what we can do then is we could do os.getEnv Pinata API key. And then, of course, we're going to have to import os. And then for our secret key, we're going to do the same thing, os.getEnv Pinata API secret. And this is how we get those two headers for uploading to Pinata. Then we're going to do a lot of the same code we did before. We're going to say with path of file path.open RB for the binary as FP. Of course, since we're using path, we're going to do from pathlib import path. We're going to do the same piece, image binary equals fp.read. Response is going to be equal to requests, which we have to import requests. Import requests. Dot post Pinata base URL plus that endpoint that we have. And for files, it's going to be equal to file. And we're going to upload a couple of things here, though. We're going to give it a file name. We're going to do the image binary, and that is getting really annoying when it keeps getting in the way. File name, image binary, and then outside of these brackets here, we're going to do comma, headers equals headers. And then we're just going to print response.json. So to have this run in Brownie, we're just going to do a def main function here. A nice little trick we can do is we can select all this text and just hit tab and it'll move it over one. And perfect, we can now run this inside of Brownie. So we can do Brownie run scripts, upload to Pinata, and perfect. We get a little output that's going to look something like this. It's going to give our IPFS hash, the pin size, the timestamp. So now if we go back to Pinata, we go to pin manager, do a little refresh here. We now see our pug has actually been uploaded to Pinata. Awesome work. We're going to keep going using the IPFS daemon to actually upload things. But if you want, you could totally swap out this upload to IPFS to use that script that we just created to upload it via Pinata instead of our own IPFS node. Anyways, this upload to IPFS is going to return this image URI. So we can go ahead then and set the image URI. It's going to be set on this collectible metadata image. And then all we have to do is dump this collectible metadata into its own file and then upload that as well to IPFS. We'll dump this to its own file by doing with open metadata file name, and we open it with a W, which means that we're going to write as file json.dump collectible metadata to the file. So we're going to have to import JSON to do this. And what this is going to do is just going to dump this dictionary as JSON to this collectible metadata file. Then we can upload to IPFS also this metadata file name. And this upload to IPFS should print out the image URI, or in this case, the metadata URI. So let's go ahead and try this out. So remember, we do need our IPFS daemon running. And let's go back to our scripts, and we'll do Brownie, run scripts, advanced, create metadata, network, rank B. And boom, okay, so here is our image URI, which if we click this, we'll be able to see looks just like this. And then here is our uploaded St. Bernard metadata file, which is fantastic. So now we have both a metadata file and we have an image URI. This is fantastic. We've uploaded both of these to our IPFS. And if we scroll over, go to our metadata file in RinkB, we'll see we have this new file in here because we've gone ahead and saved it in here. It has everything that we need. It has St. Bernard, it has the description, it has this image URI that we just created, and it has some attributes that, again, we're basically ignoring. Now, to make our lives a little bit easier, and since I've already actually uploaded these to IPFS myself a couple times, and since the hashes of these are going to be the exact same for all of us when we upload this, we're going to go ahead and just quickly refactor this to make it a little bit easier so we don't always have to have IPFS running. So in our .env, I'm going to add a new environment variable called upload IPFS, and we're going to set it equal to false. So now down here, I'm just going to say if os.getEnv upload IPFS equals true. Anyway, since we're going to do OS here, we're going to do import OS. And before this, I'm even going to do image URI equals none. And we're going to say image URI equals image URI if image URI, which again, I know this can be a little confusing, but we're saying we're setting image URI to whatever image URI is. If image URI isn't none, else we're going to create a mapping called breed to image URI of the breed. So again, since I've already uploaded them, I already know what all these image URIs for these 3 dogs are going to be. So up at the top, we're just going to create a new mapping called breed to image URI equals, I'm actually just going to go ahead and copy paste this whole thing. Now you can skip this. You don't have to refactor here. And you can just always have your daemon running and always upload to IPFS. It's a little bit quicker to not always have to do that. Again, this breed image URI is in the GitHub repo. Feel free to just copy and paste it to use it. You can even click the links to check it, check to see that those image URIs are really there. And this is what we'll use. So back down here, breed to image URI, perfect. And then we're also going to add if, again, os.get env upload IPFS equals true. Then we're also going to upload to IPFS down here. But this is to go and actually just show you how exactly we could upload all this stuff to IPFS. Since I've already done it, we're going to make it a little bit easier on ourselves. Another thing that you might do is you might actually save all these URLs to their own file, to their own JSON object, maybe inside of the metadata folder, maybe under RinkB or something. And then you could go ahead and just pull directly from those files. Same thing with the metadata. Once we upload to IPFS, we're not actually going to save these URLs anywhere. You could absolutely 100% after you run this upload to IPFS script, we go ahead and save it to a file and pull directly from there moving forward. But awesome. Okay, so we've done a lot of work here. We have uploaded to IPFS our metadata and our image URIs. So we have everything that we need to actually just set the token URI finally for our advanced collectible. We finally can call this set token URI function. So let's go ahead and do this last bit here, this last set token URI function. So let's go to scripts, advanced scripts, create a new file. We'll call it set token URI, uri.py. And this is where we're going to set the token URI. So we'll do def main. And then here we'll do a quick printf, working on network.showActive. Of course, since we're using network, we'll do from Brownie import network. We need to close that there. And let's grab the most recent advanced collectible. It's going to be equal to advanced collectible -1. Since we're using advanced collectible contract, let's import that from Brownie. Let's once again loop through all the tokens that have been deployed. So we'll do number of collectibles equals advanced collectible dot token counter. Do a quick print. You have printf, excuse me. Number of collectibles, token IDs. And let's loop through this list of collectibles again. So we'll say for each token ID, in range number of collectibles. First, we'll get the breed, saying breed equals advanced collectible dot token ID to breed of the token ID. We actually have to call this get breed function again, which luckily we generalize, so we can do from scripts dot helpful scripts import get breed. And now let's first, before we actually set the token URI, let's check to see if it already has a token URI set. So we're going to say if not advanced collectible dot token URI of token ID dot starts with HTTPS. So what this line is doing, I know it's a little bit long, is we're grabbing advanced collectible dot token URI of the token ID. So we're grabbing this token ID's token URI, and we're saying if it doesn't start with HTTPS, that means we know that it hasn't been set. So we can go ahead and print setting token URI. Let's actually make this a printf of token ID. And then we can set the token URI. So I'm actually going to generalize this out into its own function. So let's go ahead and we'll do def set token URI. And as inputs, this is going to take the token ID, the NFT contract, which is going to be our advanced collectible contract, and the token URI. So the first thing that we're going to do, we're going to say account equals get account. So we're going to grab this get account, of course, from our helpful scripts, because this set token URI is actually going to call that set token URI function. We're going to say NFT contract dot set token URI of the token ID and the token URI. Remember, this is a function that we added to our advanced collectible right here, set token URI. It takes a token ID and a token URI. And this is going to be from, of course, the account we just created. So we're going to say transaction equals that. We'll do transaction.wait. We'll wait 1 second for it, or 1 block for it. And then we'll print. We'll do a printf. Awesome. You can view your NFT at, we use that OpenSea URL, .format, NFT contract.address, comma, token ID. Then I'm just going to add another print here saying, please wait up to 20 minutes and hit refresh metadata. Hit the refresh metadata button. So now we have our set token URI function. We can add the token ID in here, the advanced collectible contract, and then we just have to add the token URI here. So since we've already uploaded, and since I've already actually uploaded all three, what you could do, and what I like to do, is just have a dictionary here so we don't always have to be pulling from something. So I have a dog metadata dictionary. It's going to be equal to, and we're going to add those different dogs in here. So St. Bernard, this St. Bernard URL. We're going to paste it here. I've actually gone ahead, like I said, and uploaded this metadata for all three dogs. So I'm just going to go ahead and copy paste all three in here. Again, we're shortcutting a little bit here, but what you could do is you could save all these metadatas to their own file, and you could just pull from that file instead of doing kind of this dog metadata dictionary. So in any case though, we're going to do dog metadata dictionary of breed, right? Because dog metadata dictionary of St. Bernard is going to be this, which again has our image URI, has everything about our dog, and is perfect. What we also might want to do is write some tests around our set token URI function, of course, but I'm just going to move on. So in any case, we've done a lot here. I'm actually going to even close down my IPFS node. And we should be just about ready for everything. So, of course, we'll run our Brownie test. Want to make sure that all our unit tests are working great, which they look like they are working fantastically. But we are ready to do a full end-to-end manual test here. And you could 100%, and I actually highly encourage you to 100%, we're just going to run these scripts in order and look to see if our stuff shows up on the OpenSea NFT marketplace. So, are you guys ready? Let's do this. So make sure, of course, your environment variables are set here. Make sure that your MetaMask for Rinkby has some ETH and has some link, and then we can go ahead and start running some of these scripts. So we'll do Brownie, run, scripts, advanced collectible, deploy and create, network, Rinkby. Integration test moment of truth. And perfect, a new token has been created. Awesome. We can even go grab this address. Let's delete all these tabs that we have opened up. And we'll go to rinkby.etherscan.io. We'll paste it in here. And we can see contract has been verified, even though we didn't verify it because it matches some other source code. We can see token counter is 1. And we can even go to token ID to breed of 0, see what breed it is. So it's breed 2. And it looks like we're getting a St. Bernard again, which is incredibly adorable. We can even go to events here and we can see the different events. Since this is verified, we can even see the name of the events. So we have our breed assigned event and we have our requested collectible event. First is an index topic of token ID, and then there's the UN8 breed. And then we have the bytes32 request ID and the address requester. Now, let's run our create metadata script here. So we'll do Brownie, run scripts, advanced, create metadata, network, Rinkby. We don't have to run create collectible since our deploy and create already does that. So now if we run our create metadata, since this is a St. Bernard again, I'm going to go ahead and get this already exists, delete to overwrite. So what I'm going to do is I'm actually going to even create another one so that I get a new NFT. So I am actually going to run this create collectible script. So we're going to do Brownie, run scripts, advanced collectible, create collectible, network Rinkby. And what this is going to do, all it's going to do is it's going to fund with some link, which it's going to be a little bit overkill with the link, but that's fine. And then we're going to do advanced collectible.create collectible. So we're just going to do 2 transactions here. Perfect. Collectible has now been created. Now I'm going to wait a solid 30 seconds to have that Chainlink VRF respond. And I'm even going to go to the contract, give it a quick refresh. Look at this token counter. Once the Chainlink VRF responds, this token counter will then be 2. Now that I see a token counter of 2 here, that means that it actually has responded. So we can now run the create metadata script. And we should have a new metadata file now. You have 2 collectibles. 0 St. Bernard already exists. Delete it to overwrite. Create a metadata file. Metadata Rinkby pug. So now if we look in metadata for Rinkby, we have a St. Bernard and we now have a pug. Awesome. So we're going to set the token URI of both of these. If I grab this contract and I go to testnets.OpenSea, testnets.OpenSea, I can paste this address in and I'll get this doggy and then this random hash here, right? And we see there are 2 token URIs deployed. Again, if they're not here, you might have to refresh, but they don't have the images, right? Because we haven't set the token URI. So we'll go back, look at the advanced collectible. We've deployed and created. We've created another collectible. We've created their metadata. Now all we have to do is set the token URI. So Brownie, run scripts, advanced collectible, set token URI, network Rinkby. And the script, it's going to loop through all of them and actually going to set those token URIs. So we have setting token URI of 0. So this transaction is doing exactly that. And it's going to go ahead and say, awesome, here's your output. And then it's going to say setting token URI of token ID 1. And that's that second transaction. And it also gives us an output to that one as well. So if we've done this correctly, and we hit refresh metadata on this testnest.opensea.io, and we do a little refresh here, we can now see our St. Bernard, which is fantastic. And then if we change this from 0 to 1, since I've deployed 2, and I refresh this one's metadata, and then refresh the page, we can now see the pug as well. Again, just keep in mind, sometimes the refreshing metadata does take some time, and you might have to wait up to 20 minutes. But for all intents and purposes, we have just deployed our NFTs, given them token URIs that aren't around centralized servers. We can now see them on an NFT marketplace like OpenSea. You can let out a big sigh of relief because you just did something fantastic that not a lot of other engineers can do. You should be incredibly proud of yourself at this point. Let's take a minute, go back over some of the new things that we've learned here.
When deploying your smart contracts on chain, we all know that those smart contracts are immutable or unchangeable. But what if I told you that they were mutable? Well, technically that wouldn't be correct. However, smart contracts actually can change all the time. When people transfer tokens, when people stake in a contract, or really do any type of functionality, those smart contracts have to update their balances and update their mappings and update their variables to reflect this. The reason that they're immutable is that the logic itself never changes and will be on chain like that forever. So technically, yes, once they are deployed, they are immutable. And this is actually one of the major benefits of smart contracts in the first place, that nobody can tamper with or screw with our smart contracts once we deploy them. However, this can be an issue if, for example, we want to upgrade our smart contract or protocol to do more things, or we want to fix some glaring bug or issue that we have. Now, even though we can't change the specific code that's been deployed to an address, we can actually do a lot more than you think. We're going to explain the different methodologies behind upgrading your smart contracts, and then we're going to show you how to do it. Now, at first glance, you might be thinking, if you can upgrade your smart contracts, then they're not really immutable then. And in a way, you'd be right. So when explaining kind of the different philosophies and patterns that we can use here, we do need to keep in mind the philosophies and decentralization implications that each one of these patterns have, as they do all have different advantages and disadvantages. And yes, some of the disadvantages here are going to affect decentrality. So we need to keep that in mind. And this is why it's so important that before you go ahead and jump in and start deploying upgradable smart contracts, you understand the trade-offs. We're going to look at 3 different ways to upgrade your smart contracts. The not really upgrading method, the social yeet, aka migrating method, and then the method that you're probably here for, which is proxies. So let's talk about the not really upgrading method, or the parameterization method, or whatever you want to call it. This is the simplest way to think about upgrading your smart contracts. And it really isn't upgrading our smart contracts because we can't really change the logic of the smart contract. Whatever logic that we've written is there. We also can't add new storage or state variables, so this is really not really upgrading, but it is something to think about. Upgrades is just parameterizing everything. Whatever logic that we've deployed is there, and that's what we're interacting with. This function means we just have a whole bunch of setter functions and we can update certain parameters. Like maybe we have a reward parameter that gives out a token at 1% every year or something like that. Maybe we have a setter function that says, hey, update that to 2% or update that to 4%. It's just a setter function that changes some variable. Now, the advantages here are obviously this is really simple to implement. The disadvantage is that if you didn't think of some logic or some functionality the first time you deployed their smart contract, that's too bad. You're stuck with it. You can't update the logic or really update anything with the parameterization, aka not really method. And the other thing you have to think about is who the admins are. Who has access to these setter functions, to these updating functions? If it's a single person, guess what? You have a centralized smart contract. Now, of course, you can add a governance contract to be the admin contract of your protocol, and that would be a decentralized way of doing this. So just keep that in mind. You can do this method, just need a governance protocol to do so. Another example of this might be a contract registry, and this is something actually that early versions of Aave used. Before you call a function, you actually check some contract registry that is updated as a parameter by somebody, and you get routed to that contract and you do your call there. Again, this really doesn't allow us to have the full functionality of upgrades here. You can argue that this registry is a mix of one of the later versions, but for all intents and purposes, this doesn't really give us that flexibility that we want for our upgrades. But some people might even think that upgrading your smart contract is ruining the decentrality. And one of the things that makes smart contracts so potent is that they are immutable, and that this is one of the benefits that they have. So there are some people who think that you shouldn't add any customization or any upgradability. You should deploy your contract and then that's it. Trilobits has actually argued that if you deploy your contract knowing that it can't be changed later, you take a little bit extra time making sure you get everything right, and there are often less security vulnerabilities because you're just setting it, forgetting it, and not looking at it again. Now, if I were to deploy a smart contract and I wanted to upgrade it with this philosophy in mind that, hey, we got to keep it immutable, we could use the social yeet method to actually upgrade to new versions. The social yeet method, or the migration method, is just when you deploy your new contract not connected to the old contract in any way, and by social convention, you tell everybody, hey, this new contract, this new one that we just deployed, yeah, this is the real one now. And it's just by convention of people migrating and over into using this new one that the upgrade is done. Hence my slang name of social yeet, because you yeet the first one out of the way and you move to the second one. I think I'm funny. This has the advantage of truly always saying, hey, this is our immutable smart contract, and this is our new one. This is really the truest definition of immutable, because since you give it no way of being upgraded in place, then if somebody calls that contract in 50,000 years in the future, it'll respond exactly the same. Another huge disadvantage here is that you have to have a totally new contract address. So if you're an ERC20 token, for example, you have to go convince all the exchanges to list your new contract address as the actual address. Keep in mind that when we do this, we do have to move the state of the first one over to the second one. So for example, if you're an ERC token moving to a new version of that ERC token, you do have to have a way to take all those mappings from the first contract and move it to the second one. Obviously, there are ways to do this since everything is on chain, but if you have a million transfer calls, I don't want to have to write the script that updates everyone's balance and figures out what everyone's balance is just so I can migrate to my new version of the contract. So there is a ton of social convention work here to do. TrailerBits has actually written a fantastic blog on upgrading from a V1 to a V2 or etc. with this yeet methodology. And they give a lot of steps for moving your storage and your state variables over to the new contract. So link in the description if you want to read that. Now let's get to our big ticket item. So in order to have a really robust upgrading mentality or philosophy, we need to have some type of methodology or framework that can update our state, keep our contract address, and allow us to update any type of logic in our smart contracts in an easy way. Which leads us to our big ticket item, the proxies. Proxies are the truest form of upgrades, since a user can keep interacting with the protocols through these proxies and not even notice that anything changed or even got updated. Now, these are also the places where you can screw up the easiest. Proxies use a lot of low-level functionality, and the main one being the delegate call functionality. Delegate call is a low-level function where the code in the target contract is executed in the context of the calling contract. And message.sender and message.value also don't change. So you understand what delegate call means now, right? Great. And in English, this means if I delegate call a function in contract B from contract A, I will do contract B's logic in contract A. So if contract B has a function that says, hey, store this value in a variable up top, I'm going to store that variable in contract A. This is the powerhouse, and this combined with the fallback function allows us to delegate all calls through a proxy contract address to some other contract. This means that I can have one proxy contract that will have the same address forever, and I can just point and route people to the correct implementation contract that has the logic. Whenever I want to upgrade, I just deploy a new implementation contract and point my proxy to that new implementation. Now, whenever a user calls a function on the proxy contract, I'm going to delegate call it to the new contract. I can just call an admin-only function on my proxy contract. Let's call it upgrade or something, and I make all the contract calls go to this new contract. When we're talking about proxies, there are 4 pieces of terminology that we want to keep in mind. First is the implementation contract. The implementation contract has all of our logic and all the pieces of our protocol. Whenever we upgrade, we actually launch a brand new implementation contract, the proxy contract. Proxy points to which implementation is the correct one and routes everyone's calls to the correct implementation contract. You can think the proxy contract sits on top of the implementations. The user is going to be making contract and function calls through the proxy contract, and then some type of admin. The admin is the one who's going to decide when to upgrade and which contract to point to. In this scenario, the other cool thing about the proxy and delegate call is that all my storage variables are going to be stored in the proxy contract and not in the implementation contract. This way, when I upgrade to a new logic contract, all of my data will stay on the proxy contract. So whenever I want to update my logic, just point to a new implementation contract. If I want to add a new storage variable or a new type of storage, I just add it in my logic contract and the proxy contract will pick it up. Now, using proxies has a couple of gotchas, and we're going to talk about the gotchas, and then we're going to talk about the different proxy contract methodologies, because yes, there are many proxy contract methodologies as well. And this is why Trilobits doesn't really recommend using upgradable proxies for your smart contracts, because they're fraught with a lot of these potential issues. Not to mention, again, you do still have some type of admin who's going to be upgrading your smart contracts. Now, if this is a governance protocol, then great, you're decentralized. But if this is a single group or entity, then we have a problem. The two biggest gotchas are storage clashes and function selector clashes. Now, what does this mean? When we use delegate call, remember, we do the logic of contract B inside contract A. So if contract B says we need to set value to 2, we go ahead and set value to 2. But these smart contracts are actually kind of dumb. We actually set the value of whatever is in the same storage location on contract A as contract B. So if our contract looks like this, and we have 2 variables in contract A, we're still going to set the first storage spot on contract A to the new value. This is really important to know because this means we can only append new storage variables in new implementation contracts, and we can't reorder or change old ones. This is called storage clashing, and in the implementations we're going to talk about, they all address this issue. The next one is called function selector clashes. When we tell our proxies to delegate call to one of these implementations, it uses what's called a function selector to find a function. The function selector is a 4-byte hash of the function name and the function signature. Don't worry about the function signature for now. Now, it's possible that a function in the implementation contract has the same function selector as an admin function in the proxy contract, which may cause you to do accidentally a whole bunch of weird stuff. For example, in this sample code in front of you, even though these functions are totally different, they actually have the same function selector. So yes, we could run into an issue where some harmless function like getPrice has the same function selector as upgrade proxy or destroy proxy or something like that. This leads to our first out of the 3 implementations of the proxy contracts. This is called the transparent proxy pattern, and this is actually going to be the pattern that we're going to be demoing to you today. In this methodology, admins are only allowed to call admin functions, and they can't call any functions in the implementation contract. And users can only call functions in the implementation contract and not any admin contracts. This way, you can't ever accidentally have one of the two swapping and having a function selector clash and you running into a big issue where you call a function you probably shouldn't have. If you're an admin, you're calling admin functions. If you're a user, you're calling implementation functions. So if you're an admin and you build some crazy awesome DeFi protocol, you better come up with a new wallet address because you can't participate. The second type of proxy we're going to talk about is the universal upgradable proxy, or the UPS. This version of upgradable contracts actually puts all the logic of upgrading in the implementation itself. This way, the Solidity compiler will actually kick out and say, hey, we got 2 functions in here that have the same function selector. This is also advantageous because we have one less read that we have to do. We no longer have to check in the proxy contract if someone is an admin or not. This saves on gas, of course. And the proxy is also a little bit smaller because of this. The issue is that if you deploy an implementation contract without any upgradable functionality, you're stuck, and it's back to the yeet method with you. And the last pattern or methodology that we're going to talk about is the diamond pattern, which does a number of things. But one of the biggest things that it does, it actually allows for multiple implementation contracts. This addresses a couple different issues. For example, if your contract is so big and it doesn't fit into the one contract maximum size, you can just have multiple contracts through this multi-implementation method. It also allows you to make more granular upgrades. Like, you don't have to always deploy and upgrade your entire smart contract. You can just upgrade little pieces of it if you've chunked them out. The disadvantages here really only seem like you have a lot more complicated code. All the proxies mentioned here have some type of Ethereum improvement proposal, and most of them are in the draft phase. There isn't really a standard here for the proxy that the whole community has landed on and says, yes, this is great, let's do it. So for all these, be sure to jump in the discussion and give your thoughts.
All right, so now that we know a lot more about upgrades and how they actually work and some different methodologies behind them, let's go ahead and learn how to actually implement some of these strategies and implement our contracts so that we can upgrade them. Now, there is a Brownie upgrades mix directly in the Brownie mixes organization that if you want to use, you absolutely can. Once again, to do that, it's just Brownie bake upgrades mix, and this will have all the code that we're going to teach you how to use right now. But let's go ahead and build this up from scratch ourselves. So we're going to go ahead and run brownie init. This, of course, we're going to create our new Brownie project here. We're going to be using the OpenZeppelin proxy contracts to actually work with this and run with this. The methodology that we're going to be working with is the transparent upgradable proxy. Now, they've been using the universal upgradable proxies a little bit more. However, the transparent upgradable proxy is really fantastic and easy to understand. So that's going to be the one that we're going to be working with here. And these are the two contracts that we're going to be importing directly from OpenZeppelin. So let's get to it. We're going to create a really simple contract that we can easily tell if it's upgraded or not. We're going to be using the exact same ones that OpenZeppelin actually uses. So let's create a new file, and this is going to be called box.sol. We're just going to have it store and retrieve some type of value. So let's give it the SPDX license identifier of MIT. So let's pick our Solidity version. And for this, we're actually going to use 0.8.0. Oftentimes, you're going to have to quickly pick up new versions of Solidity anyways. We're going to do contract box, and we're going to give it a uint256 private value. We're going to do an event called value changed. I'm going to give it a uint256 new value. Give it a function store, uint256 new value. And this is going to be a public function that anybody can call. And all we're going to do is we're going to set value to be new value. And we're going to emit this value changed event. Then we're going to have a function retrieve, and this will be a public view. And it's just going to return the uint256 value, return value. And this is going to be our whole contract. Hopefully you can understand everything that's going on in this contract. I should spell license right, shouldn't I? Now we're going to copy all of this code and create a new contract called box v2.sol. And we're going to paste it in. And box version 2 is going to be exactly the same, except we're going to add one more function called increment. This is going to be a public function, and we're going to set value equals value plus 1. And we're also going to emit a value changed event with that new value. Now this is going to be really easy for us to check to see if a contract has been upgraded or not. If we can call increment on the same address that we originally deployed box to, then this means that the contract has been upgraded. We shouldn't be able to call increment on this box contract, but we should be able to call it on box v2. Perfect. So that's all we need to do to get started. Now to actually work with the proxies and the transparent proxy that we're going to be working with, we do need to add them to our Brownie project. So we're going to create a new folder, and we're going to call it transparent proxy. And in here, we're going to add those two contracts. We're going to add one called proxyadmin.sol. And all we're going to do is we're going to grab all the code from the OpenZeppelin proxy contract and paste it right in here. Since this code is pulling directly from an OpenZeppelin package, we are going to have to fiddle with the imports a little bit to make it match so Brownie can actually compile it. And of course, since we're going to be working with another package, we have to add this dependencies to our Brownie config. So dependencies OpenZeppelin / OpenZeppelin - contracts. And for this one, we are going to actually use 4.1.0. Then we have to do compiler, soak, remappings at OpenZeppelin is going to be equal to this dependency. Now, while we're in here, we might as well do our .env so we can get our environment variables, and we'll add our wallet in here. Wallets from key, private key. We can now just have this be at OpenZeppelin / contracts access ownable.sol. And we don't need to change this at all because we're actually going to keep this transparent upgradable proxy.sol. Because this is the second contract that we're actually going to grab from OpenZeppelin. So let's create a new file. It's going to be called transparent upgradable proxy.sol. This exact text here. And we're going to copy paste this whole thing from OpenZeppelin. Boom. Paste it in here. Awesome. And then same thing here. We just have to little reverse engineer this at OpenZeppelin/contracts/proxy, ERC 1967, ERC 1967 proxy, and perfect. That is exactly where we are. So great. Now, if we've done this right, we should be able to run a quick Brownie compile. Whoops, I got to change this to box v2. Now let's run a Brownie compile. And perfect. Looks like we have compiled. We've got some stuff in build. Great, everything's working correctly. So, okay, so we have our box here, our box v2, and we have our proxy contracts as well that we can use to upgrade this box to a new version. We can even look, if we go back to proxy of OpenZeppelin, if we look at our proxy admin here, we see it has this function upgrade and call. And this call is the upgrade to and call on the proxy contract. If we look in the transparent proxy, this upgrade to and call calls upgrade to and call, which has been imported actually. So we can actually even go back, go to ERC 1967, proxy upgrade, look for that again. And this is the function that it's actually going to call. And it calls this upgrade to function, which calls this set implementation function. And all we're doing is we're doing storage slot.get address slot of this implementation slot. That value is going to be this new implementation. All it's doing is it's setting the implementation slot to being the new address that we want it to use. And we can see now, if we look in the proxy contract, the way that it actually works is it has this fallback function where it's always going to delegate all of our calls to whatever the implementation contract is. This delegate function, if we look at it, does a little bit of low-level assembly here. And it uses this low-level delegate call to send any function call or any call to this contract to the implementation contract. So this is exactly the function doing all that delegation. All right, so now that we've dug deep into the code, let's actually script this out and turn this into a script. So let's create a new file, and we'll call it 01 deploy box.sol. And this is going to be how we're actually going to deploy the box. So since this is a Brownie script, we're going to do def main, of course. Our account is going to be equal to get account, which we're going to do from scripts.helpful scripts import get account. So let's go ahead, create a new file, helpful scripts. Oops. Scripts.py. And again, we're just going to paste in that get account function from our past helpful scripts. All right, we have our get account script again. So we can just do account equals get account. Oh, this should be, sorry, it should be .py, excuse me. Do a quick print. Deploying to, we'll do network.show active. That means we got to do from Brownie import network. And then we'll do box equals box dot deploy from account. Do the little brackets here. Of course, since we're going to be deploying this contract, we also have to import that from Brownie. And perfect. This alone should just deploy the box contract, right? So this means we could do something like print box dot retrieve, and it should be 0, right? So if we run Brownie, run scripts 01 deploy, it'll deploy that. Whoops, we also got to add our .env. We don't have to put anything in here yet because we're not actually deploying to a real network. But let's go ahead and run this. I spelled retrieve wrong. It's probably good to spell things right. Let's try it again. And great. So we get 0 here. Perfect. That's exactly what we'd expect. So cool. However, though, if we run box.increment, this should error out, right? Boom, exactly. It has no attribute increment. So this is what's known as our implementation contract. This box is implemented. It's the implementation contract. Now we have to hook it up to a proxy. So let's first give it a proxy admin. And proxy admins are optional. And it's also recommended that if you do have a proxy admin and you're going to use some type of DeFi protocol, sometimes it's great to have your proxy admin be something like a multi-sig, like a Gnosis Safe, which is really fantastic. There's going to be a link in the GitHub for learning how to actually spin one of those up. Let's go ahead and do a proxy admin because they're really helpful anyways. We could, optionally, we could just set ourselves to be the proxy admin, but let's set it to be this contract. So we'll do proxy admin equals proxy admin.deploy. And again, this will be from account. And since we're using this proxy admin, we're going to import that as well. So if we look at the proxy admin, we see a couple functions here. We see like get proxy implementation, which is just going to return the address of the implementation. We have get proxy admin, who's going to be us. Change proxy admin. We have this upgrade, which is just going to call that upgrade function on the proxy. And then we have upgrade and call. Upgrade and call changes the implementation to the new implementation and then calls that initializer function. Since we want these to be proxies, you can see here that we don't have a constructor. This is intentional. Instead, we could have some type of initializer function. For example, maybe we want to have this store be our constructor. Instead of having a constructor, what we do is we call what's called our initializer function the instant we deploy this contract. For the demo here, we're just not going to have an initializer. Anyways, so now we have this proxy admin. We have the implementation contract, we have the proxy admin. Let's now hook them up to the actual proxy. First thing that we need to do actually is we need to encode the initializer function. If we wanted store to be our initializer function, like I said, we could do something like initializer equals box.store, 1. And this would be our initializer, box.store combined with 1. What we then have to do is we'd have to encode this for our proxy. If we look at our transparent upgradable proxy, if we look at the constructor, we have address logic, address admin, and data here. The logic is that implementation, right? This is going to be the address of our box. The admin is going to be ourselves, or in our case, it's going to be that proxy admin contract. And then data is going to be that initializer function. If we go into the ERC 721 proxy contract, go back to proxy, ERC 1967 upgrade, and we look at this as one's constructor, we can see that this data bit here, once this is built with this constructor, it's immediately going to call this upgrade to and call. So it's going to call this initializer. If we go to upgrade to and call, if we go back to this upgrade contract, we can see this upgrade to and call. It's going to call this address.function delegate call, new implementation data. And this is how it actually calls that initializer function. We have to actually encode this into bytes. So we have to say box.store is the function to call, and then 1 is going to be the first parameter, right? If this is what we'd want to do. So we do box encoded initializer function equals encode function data. And this is where it gets a little bit tricky, but I usually have this encode function data, once again, in my helpful scripts. So we'll do quick def encode function data, and it's going to take an initializer, which we're going to start off as none, and then any number of arguments after that. So again, this could be like, initializer equals box.store, and then the arguments could be 1, 2, 3, 4, 5, etc., or whatever, right? For us, we only have one variable that can be put into store, but this is how you would do it. And to do this, Brownie actually has a built-in function that can actually do this. We can just return initializer.encode input star args, and that's all we'd have to do. However, there is a bit of an issue when the length of the args is 0. So I've already hacked away at it for you guys. So we're just going to do if the length of the args is 0, or we're not using an initializer. Then we're going to return sutils dot 2 bytes hex string equals OX. And then we do have to import ethutil, import ethutils, and of course we'd have to pip install it with pip install ethutils. So I know I kind of rushed through that, but basically what we're doing, like I said, is we're encoding this into bytes so that our smart contracts actually know what function to call. So we're just encoding it. That's all we're doing. And if it's blank or there's no initializer, we're going to return an empty hex string. And our smart contract will understand, okay, arguments are blank here. Perfect. I've got a nice doc string in the upgrades mix that explains this even better. I'm even just going to paste it in here for now. If you'd like to pause and read this a little bit more to kind of get the full depth of what this function is really doing, feel free to do that. This is a little bit lower level Solidity and EVM stuff that we're getting into here, but it can be good to know anyways. Whew, okay, great. So now that we have this, we can go ahead and run box encoded initializer function equals encode function data, which we would import from our helpful scripts. And this is what we use when we call the constructor for our transparent upgradable proxy. I'm just going to have it be blank for now, but feel free to fiddle around and try to actually use an initializer after we run through this demo. So this box encoded initializer function is going to be blank. We're saying, hey, don't use an initializer, and that's totally fine. If we were to add some stuff to here, we would say, hey, use an initializer. So now we can actually deploy this transparent upgradable proxy. If we open this up with the constructor, we can see what we need here. So we're going to say proxy equals transparent upgradable proxy.deploy. Of course, import this from Brownie. And what are those variables that we need? Okay, we're going to need the address of the logic. This is going to be our implementation contract address. So we just say box.address because we've already deployed this, which is great. Then we're going to need our admin, which we could just say is us, but we're going to use the proxy admin .address. And then last, we need that function selector. We need that encoded function call, which for us is just blank, but we still need that. So box encoded initializer function. And then we have to add from account, of course. And I've also noticed that sometimes it's helpful to add some type of gas limit. So I'll even add a gas limit of 1, 1, 2, 3, 1, 2, 3. That's 6 zeros there. But sometimes you might be fine. But with the proxies, they sometimes have a hard time figuring out the gas limit. So I've just manually put it in here. You can if you want to. It might work fine without it. And then great, let's do a quick print function. We'll print f proxy deployed to proxy. You can now upgrade to v2. And now what we can do is on the proxy's address, we can call functions. So typically, right, if we wanted to call a function on this box contract, we do box.retrieve, or however you spell it, box.store. Let's just do box.store, right? You'd call it like this. However, we want to actually call these on the proxies, right? Because this box contract address, this box contract is always going to be the same address and can't change. The proxy code can change. We want to always call these functions to the proxy and not to the box here, right? So the way we do that is we can do proxy box equals contract.from ABI, we'll call it box, on the proxy.address, box.abi. And of course, we'll import this from Brownie. What we're doing here is we're assigning this proxy address the ABI of the box contract. And this is going to work because the proxy is going to delegate all of its calls to the box contract. Typically, if you put an ABI on top of an address that doesn't have those functions that the ABI defines, it would just error, right? But the proxy is actually going to delegate all those calls to the box. So we could actually go ahead and try something like print proxy box dot retrieve. Hopefully I spelled that right. And even though we're using the proxy address here, we are going to delegate the call to box. So let's go ahead and run this. So we'll do Brownie, run scripts, deploy box. It's going to deploy the box. It's going to deploy the admin.